Okay, last time we were trying to cheat sheet try to get a cheat sheet of rotational inertia, but we didn't get it. So let's do some rotational inertia. This is actually whatever it is. If let's say you have a piece object, right? And then this may not have a depth or whatever. Let's say this is a solid piece, and this is a little piece inside, right?
Okay.
And then this is the axis. It rotates. So you find this thing, you find its direction to this, and this is the R, right?
Yeah.
And then this is rotational inertia.
Okay.
Obviously, if it's just a piece of just like a very small mass, right? And then you find this is R, right?
Yeah.
The moment of inertia is just R squared times. Let's make this big R, okay? R squared times m, the mass of this, okay, is m r squared, right?
Yeah.
Likewise, if it's like a cylinder like this, right? Right? If the cylinder, just the skin, no mass. Actually, you can see this, right? Just the skin, no mass, nothing in the middle.
Yeah.
It's also mr squared, right? Yeah, makes sense? Because all the mass is on the outer edge, right? So all the mass has the same r, so you integrate them up. Let's say, what about if it's filled,
Okay.
right? Now we need the density of the thing, because we don't want to deal with mass. We want to deal with volume. Also uniform density, okay? Everywhere uniform density, that's assumed, okay? Yeah? So this becomes r squared dv, yeah?
Yeah.
And in the case of a cylinder, rho equals to should we just go on? Rho equals to mass divided by volume. The volume is the r squared. What is the volume?
A cylinder.
Uh-huh.
Pi r squared in the height.
Pi r squared and the height, right?
Yeah.
Okay, now let's do this r squared now dv, right? dv is when we look at this, it's dr. Let's look at the circle, right? Okay.
Yeah.
Let's call this let's call this z, right? Because x, y, z. Oh, by the way, when we're talking about x, y, z, right?
Yeah.
It's this is a right hand coordinate. In other words, your hand goes from x to y, and that's where the z is. You understand this? You understand what I'm saying? It's not this. This is x, this is y, right? This is z, right? This is not right.
Yeah.
Oh no, this is also right. X, y. Oh yeah. Let's put it the other way. X, y, right? Because x, y, z goes down. But anyway, you know what I'm saying? If this is y, this is x, z goes down.
Okay.
The way you decide this, your four fingers goes from x to y, and that's where z goes to.
X to y.
From x to y, goes from x to rotate to y. Your forefinger points to the direction the x rotates to y.
Oh.
And your thumb points to the z direction.
Okay.
Because we were talking about the cross product, right, last time?
Yeah.
Okay, now There's a dz there. We're not going to worry about. Now, for this one, right? This r, there's a dr, right? For this slice, right? There's a dr, right? Then there's r d theta. You look at this side. You look at this area, right? This side is dr, right?
Yeah.
This side is r d theta, right? Then there's r d theta, right? This you want to integrate out. Okay? M pi r squared h. I'm going to carry this. This is a pain to carry. This is all independent, obviously. R squared, no. There's three r's, right? R cubed dr, d theta, dz, right? M, right? What's this?
That's r to the power of 4 divided by 4.
R to the power of 4. This is from 0 to r, right? 0 to r. From r from 0 to r, right?
Yeah.
So 0 will go to 0. Don't worry about it. This is what? Say it again.
R to the power of 4 divided by 4.
And this is
That's
0 to 2 pi, right? You're going to do it all the way around, right? So this is?
That's beta.
No.
2 pi.
Yeah. Right? You see it, right?
Yeah.
It becomes theta. Yeah, you're right. You said right. This from 0 to h. This is?
H.
H. Okay, let's clean this up.
H cancels out.
H goes out, pi goes out, r goes out, two r's goes out, so this is r squared. This is 2, right? So you have half m r squared.
Yeah.
Okay, now this is interesting. When this is solid, this is half of this.
Yeah.
Okay? Let me ask you, if it is a stick that's all the way here, then this actually the inertia is 0. You see it? If all the mass is in the middle, then the inertia is 0. We just said that the angular momentum conserved, right?
Yeah.
I omega equals to I omega, right? If you can change the, well, let's say this is 0, this is 1, right? If you can change the inertia, you change the angular speed, right? In other words, if you do this, if you rotate, right? If you rotate with your arm out,
Yeah.
that there's R here, right? Big R, right? And then you all of a sudden you put your arm in, right? Right? You put your arm in.
Yeah.
This time the inertia becomes smaller, and you increase your angular speed, angular velocity.
Oh, yeah.
You have that feeling, right?
Yeah.
Yeah. You use that, right? When you play tennis.
Yeah.
That's how you make your when you swing. Well, you're right-handed, right?
Yeah.
When you swing your left hand to get your body to start spinning on the ground stroke, right? When you start to do when you start swinging, you get your left hand in, right, to increase your rotational speed,
Yeah.
right? So you can hit the ball harder. You get what I'm saying? Yeah. It's not to wave the hand.
Yeah, I know.
It's to take your hand in. Yeah. That's all of a sudden, because tennis, all we're talking about is in a very, very short time, how do you increase your angular velocity, right? So you can hit the damn ball. You can hit the ball hard, right?
Okay.
No. Anyway. All right. I'm sorry, okay? Anyway. Let's do some more. The other thing we want to do is a piece of rod, right? Let's say the rod is relatively small. If the axis goes along the rod, we know that's 0, right? Okay? Or if it's very, very small, all you're talking about is a disc with a very, very small r.
Yeah.
Right? Let's say that has a certain r, all you have is half m r squared, right? Which is what we just did. right? And when r is very, very small, it's very, very small.
Yeah.
Okay. Now, let's look at this. What about the axis is here? Okay. So the same thing. Rho r squared dv, right?
Yeah.
This time is, there's an area, obviously, and there's r that goes out, or x. Let's call it x, because it goes from A to B, right? We call it x. We do rotational kind of thing, and xyz we do the translational. Okay, so we call this rho r squared. Oh yeah, okay. Dx d whatever, we just call it area, because the area is not changing. This area is not changing, right? The cross-sectional area is not changing, right? Just dx times a, that's little bit here. We cut it into little slices and go, right? Now, rho equals, okay, let's calculate this first, right? Okay, r is x, yeah? When you extend out, r is x. I should do r, because this is r. Okay, let's just do r, okay, make it look better. R goes out, okay? R goes from 0, let's say this length is L, right? 0 to L, okay?
Yeah.
So what is this r squared dr? What's the, you take a goes out. What's
Yeah.
r squared dr, the integral of it?
That's 4 to the power of 3 divided by
Right.
3.
Yeah. This is rho r3 a, right?
Yeah.
For this, the volume of this is a times L that, right? This is the volume. And m divided volume, that's the rho, right?
Yeah.
Okay, we put it in. This equals to m a l. R, this is L, right? R is L. L 3 a, right?
Yeah.
So this equals to cancel out the a and L r m r squared, right? Now,
Yeah.
so this is half. This is 1/3. This is even less, right? That's because what? Because in the disk, I'm just explaining to you, so we can do less time. The more mass outside, less mass inside.
Yeah.
Yeah. If you draw a circle here, right? This is shorter than a big circle, right? So the more mass is concentrated outside than the stick, which is the same everywhere. So the inertia here is less.
Okay.
Okay. Now let's look at if the axis, rotational axis, is in the middle here. Okay. Let's look at this again. This time we should do better, right? Now, since you integrate this side and this side is the same, we'll just do one side.
Okay.
Yeah. So it's 2 times rho. This is times 0 to half an L, right? Because you only do half.
Yeah.
2 times this, right? R squared dr a, right? Okay, same thing, right? Instead of this is m2 m a l, right?
Yeah.
So instead of this r equals to L, now r equals to half an L. They only go out half an L, right? So it's L divided by 8, right? This equals to, of course, there's a 4 comes over. Where's the 3? Okay, there's the 3. This 3 I forgot, okay.
Oh, yeah.
And instead of just the 3, there's a 8, there's a 2. So it's 4.
And that's 12.
See that?
Yeah.
Because when you run in the middle, right? Instead of there's the other half is here, right? You put the half all the way to the inside. compare to this. Compare to if your axis is here, right? Just look at this half, right? This half is out there.
Yeah.
When you look at the middle, what you're doing is, if you look at here, right, you take this half in, right? You put this half actually on the other side, but it doesn't really matter which side,
Okay.
right?
Yeah.
That you really, really reduce. You really, really reduce the inertia, rotational inertia, right? That all makes sense, right?
Yeah.
Okay, let's do one more, huh? Sphere.
Yeah.
Can you do this one? No. Okay, I do it. That's okay. Sphere, right? We'll do it your way, okay? I like cosine and sine. You like r squared minus whatever.
I like cosine and sine. It makes it easier.
Okay. Actually, this one I think cosine and sine is not making it easier.
Or never mind.
Okay. Now you rotate this, right? We know the disk,
Yeah.
which is half mr, right? So for this disk, which is the dz, right? Right? There is it's a half. Okay, we have to deal with the m, right? Let's see how we do this. Okay. We still do it. Let's not shortcut. Okay, let's shortcut. Let's do it the other way. Okay. This is r squared dv rho, right?
Yeah.
This is the same thing, right? Now we split this up into r squared. Let's see. Actually, let's do it this way. For a disk, let's just call for the dz, right?
Yeah.
For the dz, let's not worry about rho for a second. For the dz, right? There is a let's just call this y. Let's just call this y, right? From here to here, this is the y, right?
Okay.
This is a z. This is z. This is the y. Okay.
Okay.
Yeah. Now, for this little disk, right?
Yeah.
It's dz half of pi r. You see this? The area of this is
Pi squared times
pi
dz.
y squared.
Oh,
times
pi
dz,
y squared. Yeah.
right? Pi y squared dz, right? Pi y squared dz, dz. This is the volume of this little thing,
Yeah.
right? You times rho, this becomes the mass, right? Now we know that this is half mr squared, right? So now this is m, right?
Yeah.
This is dm essentially. This is dm essentially. So now we put half r is y, right?
Yeah.
Half m y squared, right?
Yeah.
We want to integrate this. Okay. Before we do that, the rho equals to, let's deal with this later. Okay. This is
Take the fourth and
Why?
the pi out.
Why is this half in here? is, let's do this again. Pi, this is pi y squared dz, that's this volume, right?
Yeah.
Volume times rho is the mass.
Yeah.
This half doesn't belong here anyway, right?
Mm-hmm.
And then it's 2 half mr squared, right? That's the moment of inertia of this thing. Now we have the dz, we just integrate on dz.
Yeah.
Okay. Half is constant, we take it out. Rho is constant, we'll take it out. Pi constant, we'll take it out. Now we have y,
dz.
right?
Yeah.
And y is r theta. We're just talking about the theta business, right? This is theta, right?
Yeah.
Y is actually, or z, z is r, z is r sine theta, right? Y is r cosine theta, right?
Yeah.
You can put this in to solve it. Then theta goes from minus pi over 2 to plus pi over 2. Okay? And we're going to do it your way, which is to do this. I like this way, but in this case, actually, this way is maybe a little bit easier, but not very much. Anyway, it doesn't matter, really. So we do this, we just write this half rho pi. This is r squared minus z squared dz, right?
Yeah.
Because y squared equals to r squared